Right. Good afternoon, everyone, and welcome to our fourth Stellar Lecture Series lecture. And our speaker today is Professor Philippa Browning, who's a professor of astrophysics at the University of Manchester and Jodrell Bank Centre for Astrophysics. She obtained her PhD in applied mathematics in St Andrews and started working as a lecturer in Manchester shortly after. She has been the chair of the Institute of Plasma Physics and the UK Physics Council, as well as a member of the Royal Astronomical Society Council. And her research focuses on modeling of solar plasmas. Today, she's speaking about solar flares, which are the most powerful explosions in the solar system, and everything that they can teach us about the sun.
Okay.
Thank you.
Thank you. So, hello everyone, and thanks for coming and giving up your lunch break or whatever. And if I could just, at the beginning, just quickly apologise that I am actually expecting someone to come to the door with a tablet. It's actually someone from work, and it's the tablet that I'll be able to use for, tutorials and stuff. So I will have to dash to the door and collect that. And they were supposed to come earlier, but they didn't. So that's life. We're all working at home. So today I'm going to tell you about solar flares, and as the title says, they're the most powerful explosions in the solar system. Obviously not the most powerful solar systems in the universe by a long shot, but I say for the solar system, they're as big as it gets, and everyone always likes to talk about explosions, so I hope you'll find that interesting. I'm going to give you, it's going to be quite a sort of qualitative, descriptive sort of overview. Obviously, there is a lot of maths, a lot of detailed physics in all this, which really is the subject of my research, but I'm going to, keep this fairly, hopefully fairly low key, because, we're all in our lunch breaks. So what I'm going to talk about, I'm going to begin by a very brief introduction to the sun, perhaps more aimed as if there's, some non-physics students among you. And then I'm going to answer a series of questions, or at least partially answer. First of all, what is the sun made of? And then obviously mainly I'm going to focus on solar flares. So I'm going to talk about, what is a flare? How do they happen? But I'll talk quite a bit about how the sun affects the Earth and the idea of space weather. And it turns out if we start to understand flares, we can also answer another question as well, which is why is the corona so hot? And around there, I'll talk a little bit more specifically about my own research. And at the end, I'll just tell you really, what's coming soon, what are the exciting things to look out for. And there will be some time at the end to ask questions, so please do save up some questions. So I'm sure, most of you know this, but here is the sun. It's a pretty ordinary, smallish, middle-aged sort of star.
Wait, excuse me, sorry. We cannot see the PowerPoint. Well, at least I can't.
That's odd. Wait a sec, I'll stop share and start share again. Can you see it? Could you never see it now? Can you see it now?
Yes, can see it now.
Yeah. Okay. Thanks for that. Whoops. So So this was the outline of what I'm going to talk about. And I say the focus obviously on solar flares. And so to begin by introducing the sun, we have the sun, obviously a main sequence star. So the energy is generated in the core by fusion. Temperature there about 16 million degrees. The energy gets out through radiation and convection, but what I want to focus on really are these outer layers. So really starting here at the visible surface, the photosphere. And the visible surface, the photosphere, this is quite a recent picture from the DKIST telescope that I'll mention briefly at the end. And you can see it's got this sort of honeycomb structure, which is associated with the convection. So the energy is getting out through convection. Basically hot fluid is rising, cool fluid is sinking, and that kind of arranges itself into this sort of honeycomb pattern. And this is a very high resolution picture, and you can also see how it's sort of dynamic. Basically the pattern of the cells changes. And importantly, the temperature in the photosphere is about 6,000 degrees. So if we move quickly upwards into the corona, which is the bit I'm mostly interested in, this is a very beautiful image from one of the recent solar eclipses, the one that was visible in the United States. And even in this total eclipse image, you can see there's actually a lot of fine structure, like these rays and kind of loops and helmet streamers and so on. And key things about the corona. The first thing is that its temperature is about 1 or 2 million degrees. That's obviously much hotter than the photosphere. If you remember, that was only 6,000 degrees. And you should find that very surprising, that it actually gets hotter as you go up into the atmosphere, and we'll return to that later. The other thing about the corona is it's not static. It's actually streaming out into space as what we call the solar wind, and that very quickly becomes a supersonic flow. And at the Earth's orbit, the speed of the solar wind is typically about 400 kilometers per second. That also tells you, by the way, that we are living in the solar wind, or basically in the corona. So the Earth is essentially inside the corona. So the corona is really our own space environment. It's not just something that we, as it were, look at. It's something that we actually live inside. Whoops, sorry. So still briefly on the subject of eclipses, here's a less sort of beautiful eclipse image, but now combined with a couple of space telescope images as well, showing you the outer corona and the disk of the sun. And the reason why I tend to show this one in talks, although it's not such a good picture, is because this is one of the 2 eclipses that I got to see myself, but I would say it was rather disappointing from my point of view. So this is the best picture I got, and you can just see the moon and the crescent of the sun before it's blocked out for totality. Hang on, it's my tablet. Sorry, that's done. So as you can see, the weather wasn't great and everything was kind of blocked by clouds, so I never got to see the corona. Oh well. However, not just because of possible bad weather or even the infrequency of eclipses, but it turns out that really to observe the corona, the best thing is to go into space. And the main reason for that is actually because the corona is so hot, its predominant emission is in X-rays. And those X-rays don't penetrate the Earth's atmosphere, which in one way is good news for us, because I guess they'd be very dangerous for us. But it does mean that if you want to see the X-rays and the extreme ultraviolet, you have to put telescopes into space. And here are a couple of examples. Hinode, and notice the X-ray telescope, among other instruments, and Solar Dynamics Observatory, which has these 4 telescopes, atmospheric imaging assembly, looking in different wavelengths. So you can see the different filters corresponding to different wavelengths. And if we look at the sun using one of these telescopes, so here is the a movie from atmospheric imaging assembly, and it's actually a composite of 3 different wavelengths, and the different wavelengths essentially correspond to different temperatures. So the blue is the coolest, the green is sort of medium, and the red is the hottest. So you can see the corona's got lots of structure. It's not in any sense just a sort of uniform, we're not talking about a spherically symmetric body, which is something quite complicated. And it's also changing a lot in time as well. If we look at this more in close-up, and this is now just in a single wavelength, again from Solar Dynamics Observatory, you can see some of this, both the fine structure, in particular these things we call loops, and a rather complicated set of loops over here, and also the way that it's really constantly sort of changing in time, all sorts of sort of flickerings and flashes and brightenings. So in order to understand this complexity, the first question we have to answer is, what is the sun made of? And one way of answering that question is to say that it's made of plasma, which is the 4th state of matter. And most of the time, if you're doing a physics degree, you spend a lot of time studying solids, liquids and gases. But if you heat a gas up even further or add more energy to it, you tear the atoms apart into a plasma, and a plasma is a sea of positively charged ions and negatively charged electrons. And if you want to learn more about plasmas, there is a course that you can take on astrophysical and fusion plasmas. But all you need to really know now is, because a plasma consists of charged particles, just basically protons and electrons mainly, those charged particles interact very strongly with magnetic fields. And actually everything that we really see in the solar corona is to do with this interaction. And if I play through this movie, which again comes from Solar Dynamics Observatory, you can see the black and white is the magnetic field measured on the photosphere. So basically white is magnetic field lines coming towards you, black is magnetic field lines going away from you, and we're fading from that to the basically plasma in the corona. And you can see they are very sort of strongly correlated. So it's the magnetic field that's determining what the plasma does. And actually, even more generally, really all the structure and activity we see in the solar atmosphere is controlled by the magnetic field. It is magnetically dominated. So to illustrate this a little bit more, going back to that eclipse in 2017, here is a simulation predicting what the eclipse would look like. So this is a prediction. This is what the eclipse actually looked like. And you can see they did kind of pretty well, not perfect, but it's close. And in order to do that, they did a very complex simulation of the magnetic field, using measured magnetic fields on the photosphere and extrapolating and then sort of taking that forward in time. And here is the magnetic field. And it is this, again, this magnetic field structure, which is, if you like, sort of creating the visible corona as we see it. So another way of looking at this, you will all have done perhaps way back when you were at school, the experiment when you scatter iron filings around a magnet, and that enables you in some sense to see the magnetic field. And at a basic level we get very similar structures in the corona. So you can see here a very nice set of loops which really looks almost exactly like the bar magnet. So this is what we would call a bipolar region, in which we have a sort of north and a south, or a pair of a magnetic source and sink, as it were. But of course it's plasma, not iron filings. So if we look at the sun today, it's actually not hugely exciting at the moment, and that's because we're still fairly low in the solar cycle. But we can see we've got these sort of two relatively strong magnetic field regions, which are giving us some loops in the corona, and you can see these are rather nice simple sort of bipolar regions, so like in some sense your bar magnet, like, you know, here's a north pole, here's a south pole. If we look at the visible surface at the moment, there's nothing, but as these regions become stronger, they might well be associated with sunspots, but it happens there are no sunspots at the moment. So let me come now to solar flares, and to discuss flares, let's first of all go back a little bit in history, and we can go back to 1859, where this guy, Richard Carrington, was at his observatory, which I think was down in Surrey, I always get Surrey and Sussex mixed up, but one of those. So he had his nice observatory at home, and he was watching the sun every day and basically drawing what he saw. And he observed something he'd never seen before, these two very bright regions labelled sort of A and B on the figure. And these were two very strong, I say, brightenings of sort of white light. And he'd never seen anything like it before, but he sort of noted it down. But then over the next day or so, all sorts of things happened, literally all around the world. This ship called the Southern Cross was sailing in tropical waters and reported St Elmo's fire jumping between the masts and seeing aurora. People reported aurora even at very low latitudes, right down in the tropics, hugely unusually. They also had telegraph networks for sending messages. So here's a map as it was in 1854. And here's a picture of one. You can see these elegantly dressed Victorian ladies, you know, typing, you know, I guess sort of something like Morse code to send signals. And fires broke out in these offices, and people got electric shocks, and one telegraph operator was even knocked unconscious by an electric shock. And measurements of the Earth's magnetic field from places as far apart as Kew to Bombay measured a strong spike in the Earth's magnetic field. Again, something quite unprecedented. So Carrington speculated that all these things that had been observed on the Earth, the currents, the auroral activity, the magnetic changes, were something to do with what he'd observed on the Sun. But of course he couldn't be sure, and he famously said that one swallow doesn't make a summer. But in fact, of course, he was right, and we now know that what he had seen was, this is really the first documented observations of a solar flare. And as it turns out, a particularly large one, in fact, larger than we have ever seen since. So, what is a flare then? Well, a flare, as I said, is about a large explosion in the solar atmosphere. And this shows you this huge burst of extreme ultraviolet and sort of soft X-rays going on, in this case, in these loops on the centre of the disk. So you see it sort of build up, and then a huge, really flash of radiation. And the energy is about 3 times 10 to the 25th joules, and that is about 100,000 times the world annual energy consumption. So this is a big explosion. Here is a more complicated flare, and a particularly large one. And you can see this one is really quite complex. I'll play it through again, but you can see the flare sort of goes off here. What you then see is the loops kind of light up almost like one after another. So like a sort of, I would think like the sort of Christmas lights being switched on in sequence. You may also see something being thrown off into space around here, and we'll come back to that in a moment. And so you can see it's almost like a kind of chain reaction. If you look very carefully, you may see also some disturbances propagating away, something like a seismic wave. So I'll show that again. So there it goes. There you see the ejection just went off, and then the loops sort of lighting up, sort of one after another. So that's a particularly large and complex flare affecting a large region. So what's going on? Well, we are seeing emissions of electromagnetic radiation actually pretty well right across the spectrum, from radio waves at one end to hard X-rays or even gamma rays at the other. And this is being caused by heating of the plasmas to temperature of 10 million degrees or more, and also beams of accelerated charged particles, accelerated to sort of relativistic speeds, so quite close, significant fractions of the speed of light. So we've got very hot plasma, very high energy particles giving us radiation across the spectrum. And what's causing this? Well, there's only really one thing in the corona that's got enough energy to do all this, and that's the magnetic field. So we believe it's a release of stored magnetic energy. And the idea is somehow you build up energy in the magnetic field. If you imagine, for example, and actually this is a pretty good analogy, stretching a rubber band. If you stretch and stretch a rubber band, if you stretch it too much, it will snap. And it's kind of like that with the magnetic field. However, magnetic fields can't just snap. It turns out all they can do is rejoin in a different configuration. And so the process of energy release we call magnetic reconnection. And we can see oppositely directed field lines being pushed together, and in this localized region they break and reconnect and sort of come out with a different connectivity. And this process releases stored magnetic energy, it heats the plasma, and it also creates very strong electric fields which can accelerate charged particles. And the way we might think this might work in a flare is we have an eruption of this twisted magnetic flux tube. As this erupts, it stretches the magnetic field lines, and you can see where they're stretched, you've got oppositely directed field lines kind of pushed together, and that's where you get the reconnection, which changes the configuration of the magnetic field, releases energy and heats the plasma. And shown in red here is newly reconnected and heated field lines. So what we actually see in the movies I showed you a moment ago is something like this red loop. And then one loop after another is heated as the reconnection proceeds. Now, so you may have noticed in the previous movie something being ejected into space. And this is really like a catapulting of plasma by the breaking magnetic field lines. And this is a nice example here. So we call this a coronal mass ejection. And again, it's the release of stored magnetic energy, which is catapulting plasma into space. Now, I also mentioned these high energy particles. It turns out flares produce large numbers of very high energy electrons and protons. So these should be accelerated largely in the flare energy release site, that's the reconnection site. So some of them may, as it were, whiz out along these field lines into space, and some of them may go down the field lines of the loop and crash into the solar surface. Now, because the solar surface is very dense relative to the corona, the particles are slowed down and they emit bremsstrahlung. So that gives us hard X-rays and gamma rays. But also the gyrating particles themselves will emit radio waves. So these emission, the hard X-rays, gamma rays and radio waves, are the detectable signs of these high energy particles, particularly electrons, but we can also get gamma rays and hard X-rays from protons as well, these nuclear gamma rays. So in order to do that, we have telescopes which are specially designed to look at hard X-rays and gamma rays. So this was RESI, which operated for many years and was a hard X-ray and gamma ray telescope, now defunct, but hopefully will be sort of replaced in future. And we also have various radio heliographs which specifically look at the radio emission from the sun. So here's one in Japan, one in France. So this movie is actually showing you from RESI. So the blue is quite hard to watch, but the red and the blue are contours of high energy particles as observed by RESI. The green is basically the hot plasma as observed by Solar Dynamic Observatory. And if you look very carefully, the sort of green emission is essentially outlining the magnetic field lines, and you can sort of see the reconnection happening sort of around this location here. And as the reconnection happens, you can see the high energy particles being produced. So we've got a clear connection between reconnection and high energy particles. So really going back to this picture, we are kind of course you don't see the magnetic field, but you see the plasma outlining the magnetic field. You see the magnetic field configuration changing, hence the reconnection, and we see the high energy particles in this particular movie around that reconnection site. So there they go. So that is a bit what a flare is, but as I hinted in my introduction, flares are also, and really when we talked about the Carrington event, we saw that flares can have an impact on the Earth. So the important thing about what Carrington saw is he saw something on the sun, but he also saw things happening on the Earth as well. So this brings us to the idea that the sun affects the Earth and the whole idea of space weather. So the first part of this is to understand these coronal mass ejections. As I've mentioned, flares can sort of catapult plasma into space, and what they actually throw out is a sort of big magnetized loop which expands into space. So if we look at this on a larger scale, so this is doing basically an artificial total eclipse. So the disk of the sun is blocked out, and you can see this cloud or loop of plasma sort of coming on this side here and then expanding outwards. So I'll run that through again. So there is this big coronal mass ejection, actually a sort of smaller one up the top as well, expanding away from the sun into space. Now, if you think of, we're looking at this from the Earth, or actually from the spacecraft SOHO, which was basically near the Earth, this particular coronal mass ejection was sort of going sideways, as it were. But of course, it's possible that instead of going sideways, it could come straight towards us. And that is what happens really in space weather. So here is obviously very much an artist's impression of the solar wind, and you can see here the Earth, which as I mentioned before is sitting inside the solar wind, and we are protected by a magnetic shield which to a large extent deflects the charged particles of the solar wind, but not entirely. Our magnetic shield is sort of not perfect. So space weather is really about these interactions. So you've got the sun throwing off things like coronal mass ejection, us here protected by our magnetic shield, and then what effect do these coronal mass ejections have on us if they happen to hit us? So this is an artist's impression showing us what does happen. So here is the sun again, and in a minute you'll see a coronal mass ejection go off. So it's going to be a cloud of plasma thrown out into space. And I say this one is not sort of, as it were, going sideways, it's heading straight towards the Earth, and it's going to hit the Earth. We are protected by our magnetosphere, but the magnetosphere is heavily disrupted, and actually we get reconnection and more energetic particles which propagate right down to the polar regions of the Earth. So the Earth's magnetic field is heavily disrupted by this coronal mass ejection, just as you remember was seen in the Carrington's time when they measured those spikes in the magnetic field, and that disruption creates high energy particles which can propagate, I say, right down to the atmosphere of the Earth, usually near the poles. But I say in Carrington's event, it was so big that these regions covered a large part of the Earth's surface. So that's really what space weather is. And space weather has really three elements, and all of them, in some sense, track back to solar flares. So I've already talked about these coronal mass ejections, but also the flares, as I mentioned before, produce X-rays directly, and those X-rays can affect the Earth's atmosphere and in particular cause radio blackouts. And we've mentioned the high energy particles, and those also can reach the Earth or, you know, satellites in the Earth's space environment. So these three elements, X-rays, high energy charged particles and coronal mass ejections, all of which are things which sort of, if you like, originate at the sun but can affect the Earth. And this is another movie of a coronal mass ejection, but this time it's one coming straight towards us. And so the coronal mass ejection actually hit the spacecraft, which was SOHO in this case, and these sort of white spots are when the high energy particles from the coronal mass ejection actually directly arrive at the spacecraft and sort of hit the detectors. Now, as you might have guessed from the previous movie, where we have these particles hitting the Earth near the polar regions and giving that sort of ring-like structure, that's what we call an aurora. And this is the northern lights, but could, you know, equally be the southern lights. So that forms in a ring-like region around the poles, and it's to do with both high energy particles directly from the solar wind and high energy particles created within the Earth's magnetosphere, sort of leaking down the field lines and crashing into the atmosphere in the polar regions. Again, our magnetic shield is not perfect. Now, this was all very well in Carrington's day. As I say, it caused a few fires and electric shocks in telegraph offices and so on. But now we have a lot of technology that they didn't have in those days. So the first thing is these high energy particles could be hazardous or even fatal to humans in space. So if you were an astronaut doing a spacewalk and a flare went off, it could be very dangerous. Or even in the spacecraft, it could be dangerous, or I say even fatal, if a big solar storm hits. Closer to Earth, if you're in a high-flying jet, you can receive a significant radiation dose, and actually in big solar storms, planes are grounded or diverted in order to avoid the effects. Back on the Earth's surface, here is a transformer in a power station that was destroyed by induced currents in a big solar storm in Chicago. And satellites, as you might expect, can also be strongly affected. They're obviously in space, also communication technology and power cables. So this picture shows you the whole graphic of space weather. So we've got electrons and solar flare protons, which can damage spacecraft electronics or equipment. That can affect aircraft navigation systems and give people a radiation dose. It can, the currents can affect power stations and also power transmission technology, pipelines and cables and so on. So a whole lot of different effects, and with all the technology we now have, particularly our strong dependence on satellites, solar storms were added to the National Risk Register in 2011, and since 2014 the Met Office in the UK has instituted a space weather forecast service. So we need to sort of understand and also predict these events. And one thing we might worry about is whether we could have a really big flare. We now know from the Kepler mission that some other stars that seem to be quite similar to the Sun do sometimes have really big flares, 1 million times more powerful than the largest flare. So could the Sun do the same? And even if maybe not as big as that, we certainly know we could get another Carrington flare sooner or later. What would that do with the technology we now have? And looking back in the past, people are studying using sort of geological records whether there were superflares in the sort of relatively recent past. So I'm now going to come to the question of why the corona is so hot. So I sort of alluded to this at the beginning, that the corona is 1 million degrees. And this is really one of the big unsolved problems in astrophysics. So what we do know, or pretty surely know, is that it's something to do with the magnetic field. And we put energy into the coronal field by shuffling the foot points in the corona and somehow dissipate this into heat. But there are essentially two competing theories. One idea is that it's waves. The other idea is something called nanoflares. And the idea here is that it's basically lots and lots of little mini flares that are going off all the time. So large flares that I've been talking about so far do release stored magnetic energy, but they're relatively rare. They don't happen too often. But smaller events are much more frequent. And the idea is you could have lots and lots of little tiny nanoflares, which are individually unobservable, but their combined effect is heating the corona. So I say that in this case, the energy is basically released by dissipation of electrical currents, as in an old-fashioned electric fire. But I say we may also have waves in the magnetic field, or of course, quite possibly both. So sticking to the nanoflare idea, the idea really is the coronal field may be either twisted, and perhaps we may have multiple bundles of twisted magnetic field, as shown here, or it may be tangled or braided. In either case, you have got the conditions for reconnection, and so reconnection will happen at, as it were, the tangles, or where these twisted loops interact with each other. And so one idea is that the coronal field looks maybe something like this, minus the cat, and all the tangles are where you will get magnetic field reconnection, and hence nanoflares. So still on a cat theme, that brings us to what we actually do here at Manchester. What I do is basically all in sort of modelling and computer simulation, obviously assisted, actually that's my now late cat Rowan, and I'm particularly interested at energy release in twisted magnetic fields or flux ropes, and trying to answer questions like how is the corona heated by nanoflares, how do we accelerate these high energy particles, and how does this process of magnetic reconnection work? So one line of work is that these twisted ropes become unstable to something called the kink instability, which you can actually do for yourself. If you twist and twist a rubber band, you'll find it develops sort of knots or kinks. So here's an observation of a kink instability in the lab, and here are some of our simulations showing a magnetic field which is twisted, becoming kink unstable, and generating lots of currents, and actually hence heating by reconnection. And this is a simulation of the same process in something like a single coronal loop. So we twist the magnetic field lines up, they go kink unstable, they develop lots of localized fragmented currents and reconnection really throughout the volume of this loop. And the magnetic reconnection heats the plasma and gives off X-rays. So what's shown in yellow here is basically the emission that would be seen from the heated plasma. Remember, we don't see the magnetic field, we sort of know it's there, but what we see is the X-ray emission, which here we have predicted in this model. We also got the idea we might have avalanches in the corona. Not a real avalanche with snow, but the same physical idea. And the idea of an avalanche is a bit of snow falls down, it knocks off some more snow, and then that pulls down a lot more snow, and so on. Something, if you like, more like a chain reaction. And we think the same thing can happen with magnetic fields. So here we have a cross-section of a lot of twisted magnetic fields. So I've just picked out sort of 3 of them in this diagram, but we've got a whole bundles of twisted magnetic field. One of them has got more intense currents and goes kink unstable, and once it does that, it sort of eats up all its neighbours as well. So we have a single unstable flux rope which acts as a trigger and gets the energy out of all the others, and this is what we might call a magnetic avalanche. And here we have some simulations of the same kind of process, but now just reduced to 3 tubes, one of which is unstable and 2 of which are stable. And the central tube again goes kink unstable and sort of eats up its neighbours. All the magnetic field lines get kind of mixed up and messed up through reconnection. We keep twisting it and driving it, so we're driving it at this end, but it's reconnecting, and we get a series of bursts of energy. Lots and lots. Each of these, if you like, is a nanoflare. So each burst of energy is a little nanoflare. So we have heating of the corona by what we can call a nanoflare storm. And yeah, this is, I'll probably skip over this, but this is some recent work showing calculations of the magnetic field based on data in which we predict the impact of electrons on the surface and also the hard X-rays. I'll skip that one. And we've also looked more recently at not just solar flares, but young stars, T-Tauri stars as well. They have flares which are much bigger than solar flares and emit an unusually large amount of radio emission compared with their X-rays. And we've simulated that. This is showing the distribution of high energy electrons in a giant loop in one of these stars. And from that, we're able to see how the radio spectrum and also the X-ray spectrum change in time, and very consistent with observations. So finally, I just wanted to say a little bit about what's new, what to look out for. So perhaps the first exciting thing I actually mentioned at the very beginning is DKIST, this very high resolution telescope, giving us very, very high resolution images of not just the sort of visible light, but also measurements of the velocity and the magnetic field on the solar surface. And this has got 0.1 arc second or 30 kilometer resolution, which is pretty incredible. But perhaps more excitingly still, there are two spacecraft which are currently basically visiting the sun, or at least about to. The first is Parker Solar Probe, a NASA mission, and that is using Venus gravity assist, is sort of spiraling closer and closer to the sun. And in its final 3 orbits, it will get within 8.5 solar radii of the surface. And here is the Parker Solar Probe, obviously before it was launched. And the reason for showing this picture is this is Parker himself, after whom the mission is named, who was the very great solar physicist who really discovered the solar wind, also was a co-discoverer of magnetic reconnection and the nanoflare theory of heating the solar corona. I think in this picture he was already about 91 years old, and he's still very obviously excitedly following the mission named after him as it goes closer and closer to the sun and in the solar wind. And that was the launch of Parker Solar Probe. So yeah, it's already produced a lot of interesting results showing the acceleration of energetic electrons and ions, accelerated both directly in flares and also by coronal mass ejections. And it's discovered these weird kind of kinks or hairpin bends in the magnetic field as well in the solar wind. Solar Orbiter is the sort of European mission. Similarly, it's going to go close to the sun, not as close as Parker Solar Probe, but what it will do is go out of the ecliptic plane and hence be sort of looking down on the poles. So it's giving us a view not just of the sun, looking at it as it were side on, so we predominantly see the equator, but we will see the poles as well. And the other important thing about Solar Orbiter is, okay, these are the questions. Here again is Solar Orbiter before it set off. You can see it's got actually a very large set of instruments, and it's got two kinds of instrument. It's got in situ instruments, which are mostly stuck out on this boom here, and they measure the solar wind that it is sitting in. So it will measure things like magnetic field, velocity, and so on at the actual location of the spacecraft. And it's also got remote sensing instruments which look at the sun, but obviously from much closer up than we normally are. So we'll be able to connect what we see at the sun and what we see in the solar wind where the spacecraft is. So here is some very recent results showing that all the instruments are working. And I say we've got both remote sensing images of the sun and the inner corona, and also I say these direct images, direct measurements of things like the magnetic field, the solar wind particle composition and so on at the location of the spacecraft. So here the red are the in situ instruments, the yellow are the remote sensing. So here's just one example. You can see the magnetic field measured on the surface of the sun with sort of great precision, great detail, lots of fine structure. And from that, it's possible to extrapolate the coronal magnetic field, which you can see is very sort of complex and lots of detailed structure. It also discovered these brightenings, these very small brightenings, which it called for some reason campfires, but are essentially mini flares and are at least getting closer to something like nanoflares. So the idea, we have these very small flare-like events sort of going off all the time. So I'll just to finish, just run through this movie, which is just a composite of solar orbiter data. And sorry for the dramatic music, that wasn't my choice, but Here you can see the campfires, these little flashes, but basically lots and lots of little mini flares sort of going off kind of all the time and in all sorts of locations. And that's just a still image, so a very close-up view of the corona. That's putting the whole thing together. That's showing you velocities from Doppler measurements, magnetic fields on the solar surface. Now moving out into the sort of outer corona, showing you the outer corona and looking out at the sort of white light in the heliosphere, a much larger scale picture. And yeah, I think that's all that's going to be there. It doesn't show you the in situ instruments. So I hope I've shown you that we know a lot about the sun, but there's also a lot still to learn from both these future space missions, ground-based telescopes, and theoretical studies as well. So we've still got a lot to learn about coronal heating and flares. So I hope that might be something some of you will be interested in future. So I'll stop there and be happy to answer any questions. Thank you.
Hello.
Hi.
Hi, Professor Claudia. Thank you so much for the wonderful presentation. I have two questions. One is very basic one. I have done this project where I have just tried to prove that there is a correlation between the solar sunspot cycle and coronal mass ejection. But are we able to prove the causation that the one is causing the other?
Yeah, there's certainly a connection in the sense it's probably not so much directly sunspots, but sunspots are certainly a manifestation of very strong magnetic fields, and the whole magnetic field of the sun sort of changes through a solar cycle. And so at the solar maximum you have lots of sunspots, and the magnetic field is generally much stronger and much more complex. And that's when you get generally more solar flares, also more coronal mass ejections. You know, conversely, at solar minimum, you have the field is sort of weaker and less complicated. So you have usually almost no sunspots, and flares and coronal mass ejections are certainly rarer. But it's not a simple correlation, because flares and coronal mass ejections are not necessarily caused by sunspots. And you do sometimes get flares, even big flares at solar minimum. So they are correlated, but not in a, you know, absolutely, if you like, one-to-one sort of way. But certainly there is a relation, definitely. And I say it's all to do really with the changing nature of the magnetic field.
Okay, I have another question. The question is, what is the velocity of plasma from a solar flare as it heads towards Earth?
Right, so if you think of a coronal mass ejection, well, I can't remember the velocity off the top of my head. I think it would be typically about 1,000 kilometres per second. So the normal solar wind speed is like a few hundred kilometres per second, and a coronal mass ejection is going, if you like, a bit faster than that. The other way to look at it is, I know it typically takes a coronal mass ejection about a day to get from the sun to the Earth. So knowing the distance, you could work out the speed. I mean, they do vary, you know, you get fast ones and you get slow ones, but I'd say typically a day to travel the sun-Earth distance.
Okay, and how you have prepared these simulations, means using what software? Have you used this Monte Carlo simulation?
No, most of the simulations I showed you are magnetohydrodynamic simulations. So we're solving the MHD or magnetohydrodynamic equations, which solve both the sort of fluid dynamic equations and also the evolution of the magnetic field. So it's like electromagnetism and fluid dynamics basically sort of put together. And the numerical method, essentially it's a finite difference method, but with some, well, it is a finite difference method, but you know, there are some, you know, bells and whistles to how it actually works numerically. But we also do particle simulations, and to do those we simply solve for the equation of motion, the sort of differential equations for the charged particles in electric and magnetic fields that we take from the MHD simulations.
Okay, thank you so much for the information. Thank you.
Okay.
How small? Oh, okay. The induced currents caused by, say, the Carrington event. It looked like it affected things which were quite large, like telegraph cables. Would a hard disk, an unconnected hard disk, for example, be affected by those sort of currents?
Oh, that's a good question. I don't know, to be honest, but I haven't heard anyone say that that's a problem, let's say. So I'm thinking that it does probably, the effects will be more on sort of bigger things. And I guess that's because you're looking at relatively large scale changes in the magnetic field. But I say, having said that, they did get these electric shocks in the telegraph offices, and, you know, they obviously, as it were, weren't that big, you know. And obviously on satellites, and obviously they're more vulnerable because they're actually out in space, but, you know, we certainly do get damage, if not, you know, temporary or permanent, to instruments on satellites. So yeah, that's a good question, but yeah, so I think it is possible, certainly, that things like that could be affected, but actually, to be honest, I don't know.
Yes, I have lots of data I'd like to keep, and
yes, always back it up, I think, is the
yeah. Then back up the backups.
Yes.
So we have a couple questions in the chat.
Oh yeah, let me read through those. Okay, someone has asked, Flavio has asked, do we experience on the Earth effects of solar flares with smaller magnitude than the one that happened on the 19th century? Yeah, I mean, in fact, the one that I say happened, the Carrington flare, is pretty well the biggest flare we have ever seen. And in some sense, the reason, it's not sort of surprising in a sense that the first flare that was observed was a big one, because at that point he wouldn't have observed it unless it was very big, if that makes sense, because obviously he didn't have, like, you know, modern instruments sort of thing. So yeah, but we do certainly experience, I mean, space weather effects certainly do happen. So the things like the power station transformer that was knocked out, those are obviously from a particularly big flare. And those, but things of that, you know, of that sort of scale do happen, you know, relatively frequently. So, in some sense, how often do flares happen is quite a hard question, because big ones happen quite rarely. You know, smaller ones happen more often. Not every flare, even a big flare, may or may not affect the Earth. Because if you take, for example, the coronal mass ejection, you might get a huge flare, but it throws off a coronal mass ejection that doesn't hit the Earth, and so in a sense that doesn't affect us much. And there have, relatively recently, there was a flare that was almost as big as the Carrington flare, and actually, if you like, almost affected the Earth, but actually had very little effect. And that was just to do with sort of where it went off on the sun. But I say, roughly speaking, flares are not uncommon. So particularly at solar maximum, you may get, you know, a flare every few days, even like a relatively big one. So they are not particularly rare events. You know, really big flares, you might have, you know, 1 or 2 a year, let's say. And, you know, really small flares are happening, well, like nano flares, we believe are happening all the time. So yes, if you like, small space weather events are not that uncommon, I would say. Okay, is there another, go scroll down through the chat. Is the observation of nanoflares limited only by precise detectors? Yeah, that's a good question. Sort of yes and no. I mean, in principle, if you had better instrumentation, you could detect smaller events, and to some extent that's what we think Solar Orbiter is doing. But there is perhaps a more fundamental thing with nanoflares, is because we think they are very frequent and, if you like, sort of happening all the time, then to some extent they sort of merge into each other. So if you think of a time sequence, the big flare will be like a big spike, and there's no argument that, you know, okay, that was a big spike and that was a flare. But if you now imagine you've got lots and lots of small ones, well, they kind of merge into each other, and it's a bit hard to say, well, is that, you know, you almost can't just see one nanoflare, because there will be lots of nanoflares always happening at the same time. So really, we probably have to detect them by more indirect means, if you like, thinking, well, what would be the consequences of lots of nanoflares? And actually, that's really where theory comes in. So theoretically, you can sort of say, well, okay, if there were lots of nanoflares, this is what we would see, and then, you know, people look for those signatures. So I say it has to be a little bit cleverer than just looking at the actual events. So, any more questions, or have I missed anything?
Right, maybe if people have a question afterwards, maybe they could email you with a question, if that's okay.
That's fine, sure. Yeah, be happy to do that. Yep.
Right, thank you very much, and thank you for everyone for coming.
Yeah, cheers. Thanks for the questions, guys.
Lovely.
Thanks for coming. Bye.
Thanks, Professor.
Thank you.